Hi everyone. So today I'm going to solve example number 3 in which we are going to be designing a deep member. It's the same as the previous example which we did as example number 2, but this would exemplify how to deal with a uniform distributed load. I set both examples such that the resultant becomes the same, almost the same. I think there is 10% difference. You can check it yourself. So let's get into this and then see how this would work. So the first step, as always, is to develop the model, develop the truss model. And for this, we again need to sketch two lines, one horizontal, other one vertical. One is going to be strut, the other one is going to be tie. We know from the previous example it's going to be something like that. This is going to be tension, top would be compression. Again, we need distances. You can start by assuming anything, but of course a good assumption will minimize the work. Stress block approach, call this A over 2. Again, remember the multipliers. The node at the top is CCC. CCC type of node has 0.85 multiplier. The node at the bottom is CCT. It has 0.7 multipliers. So in other words, this is more critical. It's going to need more space, larger space. The space needs to be larger than A over 2. What I'm going to be doing, A over 2 times 0.85 divided by 0.70. Previous example used a 650. If I'm not mistaken, there could be slight differences. So this is what we did. So it's a good starting point. You always would like to start with what you have done previously. So let me check the previous example just to make sure. Yeah. So, I would expect something around that number. So let's start with 650. If you want to do it again, you need to determine what location you are concentrating the UDL, because strut and tie, there is no UDL. Strut and tie only works with a point load. You need to concentrate it at a certain point, which is, for example, 3560 kilonewton, which is 630, that's UDL, times 11.3, that's the entire span, divided by 2. So this is how I get this. So pretty much I'm doing half of it, right? 630 times the span divided by 2 for that load. The distance, again, it's really up to you. You can go with, for example, L over 4 for this one. And again, same as previous example, I'm not going to repeat it. Same as previous example, in which we said C equal to T. Maybe I repeat it because some people might just watch this video before watching the other one. So let's just get this done again. So based on this, C equal to T, 3560 times the distance, 2.825 meters, minus 0.625. So I'm just calculating the moment created by these couple. 111 inches minus 25 inches, that's the lever arm, times the force. It's going to give me the moment. So I'm just converting this to newtons, and it's going to be equal to compression times 4,000 minus 1.107 A. So this is that distance. This is 4,000 minus 1.107 A. So I'm doing moment equilibrium. So the moment created by this couple should be balanced by the moment created by that couple. So I'm just making them equal, and this is the equation I got from this. And then I remember strength of materials from undergraduate studies. Stress blocks. You use this very often for any single design using sectional method. So using stress blocks, compression would be the same as, there's a coefficient which is 0.85. Concrete reduction, this is phi C, 0.7. 25 megapascal, that's concrete strength, times 400 thickness. which is 16 inches times A. You need a calculator or you need a spreadsheet because it's going to be a second degree equation to solve this. And if you do this, 366 millimeter, this definitely looks too small, because for the same sort of point load we used 650 previously. Now I got 366, so I'm not going to be using this. I suspect this is going to fail. One reason for this might be this assumption, putting this to L over 4 gave that small distance. Maybe you can try L over 3, but this is a beginning. You don't have to use what you get at this stage. If the numbers do not make much sense, you don't have to use it. So I'm going to be using again 650, and I'm going to see whether I have tons of reserve, which I don't think so. I would expect the same design as the previous example. So I'm going to be using 650 to get started. Millimeters, same as previous example, and we'll see. So L over 4 is maybe question mark, maybe you might try L over 3 and then see what you would get for A. Definitely it's going to be larger, maybe that's going to be a better approximation than L over 4. This is used very often. This is a textbook approach. There are certain approximations. This uses 1, 2, 3, 4, 5, 6 division. So this uses UDL divided by 12 approximation. So this is how I got my design. You have this handout. It divides the UDL into 12 equal segments. This is a pretty nice approximation. I don't recommend anything finer than 12. It's a good number. This is another one. This is what I started with, L over 4. I don't use this. This is too coarse. It might be somewhat unconservative in some situations, and you might see some publications showing some issues. So there are some restrictions. They say use this if you have this situation. So I never use this because the effort is similar. When I use this one, I'm going to check only the shallowest strut. So don't get scared by seeing all those diagonals. The only thing is the shallowest one. We'll check that, and that will be the only check. So it's the same effort. This only has one diagonal strut, and this is also has one diagonal strut that needs checking. So this is the one I'm using. The same approach is a foundation. So it's again in a foundation P over 12. So you do this separation. Again, you separate the load to various nodes. That's another one. So let's go with this one. So P over 12, that's going to be the load. You can definitely use AutoCAD. 593 kilonewtons. So each of them would be 593. The resultant, just for the sake of showing it, if we had a resultant, it's going to be here, L over 4, 3560. I'm not going to be doing much with it. You don't want to do it. If you only use that one, it becomes the coarse model. So I don't want to simplify it with a single load, but 6 division for this example. Of course, the most critical one, let me write it here, 593, it's going to be the shallowest strut. The challenge will be to get the angle. You have, if you sketch this in AutoCAD to scale, you are done. But if you are doing hand sketches, you have some trigonometry to do to get that angle. If you do the analysis, you know all dimensions. The tension, you can use the resultant to get the tension. So the tension here is going to be 3560 times 2200, which is this distance, 3285. I think I did some correction to this solution. Maybe you have the right numbers, so I'm going to do that correction, 3285. So this one, I'm correcting it, 3285. This is 325. That's, I think, what I choose, 325. And this one 390. So those are the two dimensions which I selected for this problem. So that's what I need at this point. But I mean, the compression at the top, the maximum compression would be the same. It's going to be minus 2384 kilonewton because tension equal to compression. That's always the case. So this is sort of a quick model, and then I can go back to step number 2. So AS, again, let me remind you the equation. T phi S Fy 2384 times 10 to the power 3, 400 megapascal, that's 58 ksi, 6623 millimeters square. Example number 2, what we used, 30 number 7. If you look at this area, which is less than the previous example, I'm going to be using less. Previously we used 10 layers of 3. You might remember I did a sketch, but for this one I can reduce it to 9 layers of 3 because that gives the area. So I'm going to be using 27 number 6. The area would be 7668, which does make sense because uniformly distributed load would have a less effect as compared to a single point load at the midspan because it's distributed. So it does make sense. I would have expected less for the uniformly distributed case. So this is what I'm using. So I'm going to say fit was checked previously. So I'm not checking that. If you remember, this was the fit we did. We used 10 layers. No problem. I mean, if 10 layers fit, 9 layers would definitely fit. You can spread S spacing in between. Usually reducing it is a problem because you don't want to go less than the minimum. We didn't have any problem with that for this problem. So you can increase it and you can get the centroid at any point. So this is already done, no problem. Fit was confirmed previously. We need to find forces because we didn't solve the truss fully. We are not going to be solving it fully. What I'm interested is only what's the tension at the tie, what's the compression at the strut, and what's the compression at the shallowest strut. We are going to be checking only the shallowest strut for this example. As you can see, nodal geometry is extremely important. You want to get this to the midpoint. If this is 31 inches, this is half of it. So again, I'm not using a single node, never. So I'm not joining everything at a single node, it's separation. So each strut has a certain tributary distance. So they are using, and the dotted lines really show what they are using. So what I'm going to be checking is this distance. So I have to calculate this distance when I do my checks because that's the distance, that's the concrete which supports this strut which has this force coming. So this is 780. Maybe your nodes already fixed. This might have been an earlier version. So this is the triangle which I'm using. And in terms of distances, I'm going to be calling it at H, and this one I'm going to be calling as V. First of all, let's calculate H, because once I find that, once I isolate that triangle, that's what I need, nothing else. Of course, if you are using a software, you would get this right away, but I'm just using hand calculation. Tributary distance, if you divide this by 6, you get 942 millimeters. So 5.5 times 942 times 5.5, because it's equally spaced and I'm here, so I'm using 5.5. What I'm measuring right now is the full distance from edge to that point. What I need to deduct is the distance this much. So this is the one which I would like to deduct from this number. The entire width is 1250 minus 1250 times 11 divided by 12, because this is divided by 12. 11, this is 12. So I'm just counting this. This is 1, 2, 3, 4, 5. It has 12, but I'm just using 11 of those, and it's going to give me, this is again a textbook approach. You will see this solution if you look at some textbooks for this type of geometry. So this is the horizontal distance. I hope it's clear. The vertical one is very similar. 3285 plus 390, because I'm looking at this distance. So I calculated the entire distance, but I need to really deduct this 1/12 of 780. 80. So it's minus 780 times 1/12th, and this is going to be coming out as 3610 millimeters. You know horizontal, you know vertical. The theta, which is extremely critical, is going to be tangent inverse vertical divided by horizontal, and you would get that pretty nice 41.8, which is theta. So once you get theta, that's pretty much it. Theta is what we need. Then we can easily get the force. The force on this strut is going to be 593 divided by sine theta, 890. So the force on my most critical strut is going to be minus 890. So I didn't really calculate the horizontal component, which is not needed. If you want to calculate, you can go ahead and you can calculate that. So perfect. We got the theta, we got the force. We are in a good shape with this. This is kilonewton, and let me show you that it's this one. I hope this is clear. So after this, I mean, the problem is pretty much finished. So once you determine geometry with UDL, the rest is just a couple of checks. Step number 3, nodal zone checks. I would like to give some lettering. Call this node at A and call this one at B. So I would start with node A. So node A is just CCC type of node. This is 0.85 F prime C. That's the limit. I'm going to be checking bearing. In other words, I'm checking. You would say that, oh, there is no bearing plate, but you don't have to. So I'm just checking crushing because this is a tributary distance. I'm just checking crushing in this region. Is this concrete would be able to carry that 593 kilonewton? So that's what I'm checking. So I'm going to say dr would be 0.85, or let's start, okay, let's start with 0.7 because that's phi c. 0.70, this is reduction, and then 0.85 times 25. So this is the routine terms. The distance would be 942, that's the distance, times thickness would be 400 for this case. So it's just a bearing check, similar to the column check I did. Oh, it's tons of, there's no problem, lots of capacity available. So this is much larger than 10 times, almost 9 times larger. I'm going to check the compressive strut. I'm going to check whether this 325 was a good assumption, whether I have enough concrete to support this force. I would bet it would be good for this problem. So I'm checking PR. It is going to be 0.70, 0.85. The beginning would be the same. The area would change only. 2 times 325, thickness 400. So this is what I'm using. If you look at this 3868 kilonewtons, what I got 2384, which is pretty nice. Nothing else to check. So node A completely passes. Again, recall I'm not checking the diagonal strut. That's the next step, step number 4. Node B, the type is with one tension, so CCT limit. Based on H though, it is 0.70 F prime C. What should I check? Let's start again with bearing check. Check the entire bearing for this concentrated force, which is support reaction 3560 kilonewton. So BR, this is the capacity, 0.70, 0.70 times 25, area 1250, thickness 400. That's the bearing plate thickness. It could be smaller, but this occupies the entire section. If you do that, let me see. Let me double check. 6125, which is pretty good. what we have 3560. So this is what I have. So the bearing passes no problem. Finally, I would like to check 390. I allocated 390 times 2 for this tension. So I'm going to check whether the width of the tie is sufficient or not. So TR would be absolutely the same multiplier, same node, everything would be the same in terms of multiplier. The area would change. 2 times 390, thickness 400. No problem, tons of capacity available, so it's a good start. So 390 was good, tension was good, node B is done successfully. So that's pretty much it for nodal zone checks. There is nothing else to check. I don't want to proceed before asking you if you have any questions about the process. If not, the next step would be critical step number 4. I'm going to be checking the diagonal strut. Angle seems to be fine. Again, this comes from the handout because there is some trigonometry involved, which is this one which I have given you already. You have 4 different formulations for strut width for these situations. Consider this to be the 5th one, which shows you how to get the distance. So we have this 780. Theta, we found it to be 41.8 degree, important parameter. So I'm going to be calculating first concrete efficiency factor minus F prime C, which is, I'm just using US units because this equation uses US units, divided by 20. This is KSI 0.67, which is, it exceeds the maximum, 0.65 max. So what I'm going to be doing is to calculate PR, which is going to be 0.70. This is concrete reduction times 0.65. This is that. Concrete strength 25 megapascal. And then the most critical multiplication would be the area. 400, we know it, thickness 400, but we gotta calculate strut width, which is, perhaps I start from left because it's going to overflow. It could be a column, it could be a wall, it could be anything. It doesn't need to be a plate. 1250 times sine 41.8 plus HA cosine 41.8 divided by 6. Again, it's dividing it equally into 6 segments because 6 struts each uses 1/6 of the area. Pretty small. Sometimes, I mean, in many cases, this gives an issue. This gives some challenge. It might fail. Thickness 400. So this is 400 thick in the out of plane direction. So no, I don't have good news. What we got 890. No, it failed. What's the overload? We have, I think it's a major overload. 890, 750, 19%. So we failed it. What are we going to do? Any suggestions? That's, I mean, yeah, that always works. Bigger bearing plate. So the issue is, you know, such a small tributary distance for that strut, which is pretty shallow, but it's not shallow actually, it's pretty good angle. So think about that. If you have even shallower angles, it's always going to give some trouble. So, I mean, some options, larger bearing plate, definitely. This is, I mean, somebody might tell you that, oh, this is already large. If you have some possibility for a larger, even larger one, go for it. Of course, maybe increase F prime C because F prime C is here. That could be an option. Or maybe increase section thickness, which is this 400. Perhaps not all at the same time, but maybe a combination of it. Maybe you only do one of these. Definitely, I mean, if it's a new design, you have multiple options. You can do all of these, but sometimes you are stuck. Sometimes it's an existing design, it doesn't pass, and you want to get the most efficient design. Looking at this, it looks like node A 325 was a little bit too much. So you can reduce that. So you can get the centroid of the strut closer to the edge as much as possible, maybe go with 300, maybe 280, plus similar approach for the centroid of the reinforcement. So this was also a little bit too much. You can, if you reduce that, you have to be careful, maybe not this one, because if you reduce that, you are going to be losing 780. You don't want to do it, so don't reduce it, because if you look at the equation, you definitely, you would be fighting against yourself. If you reduce this, this is going to get reduced, so don't touch it. You can even increase it. If you want to increase the centroid of the rebar, you can do it. That's going to be, maybe shift the model a little bit above, maybe 25 millimeter above from both ends. This becomes 300, this becomes, you know, maybe 425-ish, and see how it works. So if it's an existing structures, you have some calculation to do. The overload is not huge. If you see a major like 50%, 60% overload, it's not a good approach. I don't think it would fail, but in this situation, maybe 18% overload, maybe you'll reduce it to 4-5%, and it's an existing structures. You might say that it's acceptable 4% overload, and you might pass it for that situation. So, but I would proceed. I'm not going to fix it. So I think we are pretty close to finishing this. We can finish this before we take a break. So again, I'm not checking the top end, as you know. The reason, the bottom end, it is pretty narrow. Top end of the strut, it's pretty wide, so it's going to pass. So I'm not checking the top end. I'm only checking the bottom end. Also, the top end is compression, compression, compression. So this is the governing. This is the governing situation. I'm going to check bar anchorage to make sure whether it is enough. So you see the compression is going into the support, and I have to check it at this point. So this is the point I'm checking. So if you look at my enlarged section, this dotted line is the same as this dotted line. So this angle is not theta, but that angle is this angle, which comes out to be 39.9 degree. So you can calculate that using trigonometry. It's going to be less than theta, so it makes sense. So based on that, oh, it's already calculated. This is 390. Again, I'm going to fix this. So this distance here would be 390. Let's recalculate. Cotangent 39.9. Let's just do this. 390 times 1 over tangent 39.9, 466. Yeah. Edge cover, it was same as before. It's, I think, close to 2 inches, which is 40 millimeter side cover. So this distance LD available. Length available for development would be 1250. That's the bearing plate size, plus 466 minus 40, 1586 millimeter. Required development length for straight bar that we are using, 1045, which is much shorter. Straight bar is good, no hooks needed. So again, I'm not checking development at the nodal centroid, but I'm always checking it at the intersection, at the edge, because compression is anchoring it. Compression is always beneficial, and it's going to be helping with anchorage. We are going to be providing 0.3% both ways. So for this situation, vertical would be the same as horizontal. Area bar BW, which is section width, times S, would be larger than 0.3%. So I used 2 layers because it's a thin section, one attached to each face, would be 400 thick times spacing 0.3 times 10 to the power 3. So based on this, I got use either number 4 at 200 or number 5 at 300. This would be better in terms of serviceability based on the calculation. So these are for both vertical and horizontal. Step number 7, if you have any checks So I would say do any additional checks here. Step number 8, very similar to the previous example. So we can just modify this, what we used. So we are using number 6, so it's substantially less amount of reinforcement needed for uniform distributed situation. So you are going to be adjusting that. You are going to be adjusting the centroid of the reinforcement. Crack control reinforcement, we are using number 4 at 200, which is the same as that one. So it's pretty much very similar, almost identical design, except the main reinforcement is going to be less for this situation. That's pretty much it for this example.